430,000 miles per hour, into the sun's atmosphere. Then 2 days of silence. Was the machine still alive? And why was it there? Because the sun's atmosphere burns up to 300 times hotter than its own surface, and after 80 years there are 3 suspects: magnetic waves, microscopic explosions called nanoflares, or zigzag field reversals found in numbers no model predicted. On December 26th, one radio tone reached Earth. Alive, but survival was never the headline. The data this machine carried home does not match the models. Christmas Eve, 2024. NASA's Mission Control in Maryland. Engineers staring at screens showing nothing. The Parker Solar Probe, the size of a small car, had been flying inside the atmosphere of a star on its own. Walk away from a campfire and the air cools. Climb away from the sun's surface and the temperature explodes into the millions. The last time our star misbehaved, telegraph wires caught fire. The room at the Johns Hopkins Applied Physics Laboratory did not look like a place where history gets made. Rows of consoles, coffee going cold, a wall clock ticking through the morning of December 24th, 2024, while most of the country wrapped presents. The people in that room had spent more than a decade building one machine, and that machine was now closer to the sun than anything humans have ever made. They could not talk to it. They could not steer it. They could not even confirm it still existed. This part was planned. Near the sun, the corona pours out so much electromagnetic noise that the probe's radio signal drowns in it, the way a whisper drowns at a rock concert. The team knew the blackout was coming. Knowing did not make the silence easier. Somewhere on the far side of that glare, their spacecraft was executing its closest pass on autopilot, 3.8 million miles above the solar surface, moving at 430,000 miles per hour. At that speed, you would cross from New York to Los Angeles in about 20 seconds. No commands could reach it. No data could leave it. If something failed, the first evidence would be silence that simply never ended. There was a particular cruelty to the physics of it. Even in perfect health, the probe could not call home until its orbit carried it out of the glare. The fastest object humanity has ever built, and all anyone could do was watch a clock. Around the building, the holiday went on as if nothing was happening. Inside that room, men and women who had given 10 years of their careers to one machine rationed their coffee and said very little. So they waited through Christmas. Then, late on December 26th, a station picked up a single beacon tone. It carried no data and no images, just a short radio pulse that meant, "I am here, I am operational." Engineers who had carried this mission for years stood in that room and let themselves breathe. 2 days of institutional calm cracked open in a single second of radio. If that moment gives you chills, this is exactly the story to share with the one person you know who still thinks nothing exciting happens in space anymore, because the tone was only the receipt. The package arrived in January, when the science data started downloading. And what was in that package is the real story. The machine had been taking measurements inside the atmosphere of a star, in a place our physics says it should understand, and the numbers were arguing back. Here is the crime scene. The surface of the sun, the bright disk you actually see at sunset, runs at about 10,000 degrees Fahrenheit. Hot beyond anything in daily life, but well behaved. Physics is comfortable there. The problem starts above it. Stretching millions of miles out from that surface is the corona, a halo of thin, glowing plasma. You have seen it with your own eyes if you have ever watched a total eclipse, that ghostly white crown around the blacked-out sun. For most of history, observers guessed it was some trick of the moon's atmosphere. It is not. It is the sun's own outer air, and it refuses to behave. Measure its temperature and the numbers come back between 1 and 3 million degrees, up to 300 times hotter than the surface below it. Sit with that for a second because it breaks the most basic rule of heat you know. Heat flows from hot to cold. Step back from a fire and you get colder every time, no exceptions. The sun runs this rule in reverse. The further you climb from the furnace, the hotter it gets. It is as if you backed away from a campfire and your jacket burst into flame. Astronomers first ran into this in the late 1930s and early 1940s when strange green light from the corona turned out to be iron atoms stripped of half their electrons, something only millions of degrees can do. 80 years later, the question still has no settled answer. Physicists call it the coronal heating problem, and it is one of the oldest unsolved cases in astronomy. If you enjoy watching a tidy law of nature get publicly embarrassed, that like button is right there. But this is not just a puzzle for textbooks. That overheated corona is where the solar wind is born, the stream of charged particles that blows across the entire solar system at 200 to 500 miles per second and slams into Earth's magnetic field. When it hits hard, satellites glitch, radio fades, and power grids strain. In March 1989, a storm a fraction of Carrington's size collapsed the power grid of Quebec in about 90 seconds and left 6 million people in the dark. Understanding why the corona burns is understanding the weather that our entire electronic civilization floats in. If you want to know how this case ends, subscribe, because this channel covers the universe the way detectives cover a crime scene. 3 suspects have been under investigation for decades. Only one of them keeps showing up in Parker's data. Suspect number 1. Waves. The sun's surface boils like a pot, and all that churning shakes the magnetic field lines that rise out of it. Shake a field line and you launch a wave along it, the way a flick of your wrist sends a ripple down a garden hose. These are called Alfvén waves, after the Swedish physicist who predicted them, and they carry real energy upward into the corona. If enough of that wave energy breaks and dumps its heat up there, the mystery is solved. That is the theory. The waves exist. Parker has flown through them. What nobody has proven is whether they deliver enough heat in the right places to do the whole job. A suspect carrying enough cash, in other words, but with no receipt placing the money at the scene. Suspect number 2, Nanoflares. Not one big furnace, but billions of tiny ones. The idea goes back to the physicist Eugene Parker himself, the man the probe is named after. Magnetic field lines above the surface get twisted, tangled, and stressed until they snap and reconnect, and every snap releases a burst of energy. Each individual flash is small by solar standards. Add up billions of them, firing constantly across the whole star, and you could cook a corona. The catch: they would be far too small to see individually, so the case for them is statistical, inferred from the heat they would leave behind. A suspect with no fingerprints, only a pattern. For decades, those two camps argued past each other, walls versus explosions, each holding evidence the other could not explain away. What the argument needed was a witness from inside the scene. And then there is suspect number 3, the one nobody invited. When Parker began skimming closer to the sun than any machine before it, its instruments kept recording something strange. The magnetic field would suddenly whip around, point backward toward the sun for seconds or minutes, then snap back like an S-shaped kink traveling outward. Scientists called them switchbacks. A few oddities like that were expected. Parker found the solar wind near the sun absolutely littered with them, in numbers no model had predicted. These were not stray glitches at the edge of the data. They were everywhere it flew. Here is where the case gets interesting. These 3 suspects are not strangers. Waves can steepen and snap. Reconnection can launch waves. Switchbacks may be the visible scar of both. Drop a comment with the suspect you would bet on, because the evidence is about to get physical. Before any of that evidence could exist, somebody had to solve a more basic problem. How do you park a machine inside a furnace and have it live? The answer rides on the front of the spacecraft, and it is almost insultingly simple. A shield, 4.5 inches thick. 2 skins of carbon composite sandwiching a core of carbon foam that is 97% empty air, the whole thing capped with white ceramic paint to bounce sunlight away. That is it, 4.5 inches between the mission and oblivion. During the closest passes, the sun-facing side of that shield cooks at around 2,500 degrees Fahrenheit, hot enough to melt steel. A few feet behind it, in the shield's shadow, the instruments sit at about 85 degrees, roughly the temperature of a pleasant afternoon in Florida. How is that even possible when the corona around the spacecraft measures in the millions of degrees? Because temperature and heat are not the same thing, and the difference is the whole ballgame. Temperature measures how fast particles are moving. Heat is how much energy they actually hand over when they hit you. The corona is fantastically hot, but fantastically empty, a near vacuum. Its particles are screaming fast, but there are so few of them that the total energy delivered to the shield stays manageable. The probe is not swimming in lava. It is being struck by a blizzard with almost no snowflakes. The engineers had one more trick. At 430,000 miles per hour, thermal stress tries to rip a rigid spacecraft apart, so they built the frame with joints that flex. The machine bends so it does not break. Even the solar panels needed saving. They make the probe's electricity from the same sunlight that is trying to destroy it, so the arrays are cooled by water circulating behind them. Plumbing, in other words, flying through the atmosphere of a star. Getting it down there took patience on a planetary scale. You cannot just aim at the sun and fall. A spacecraft leaving Earth carries our orbital speed and overshoots. So Parker spent 6 years threading past Venus, 7 separate flybys. Each one was a brush of Venusian gravity that bled off speed and wound the orbit tighter, like reeling in a fish that weighs as much as a star system. 6 years, 7 passes, each one shaving off speed the spacecraft could never have shed on its own. The 7th and final flyby came on November 6th, 2024. After that, there was nothing left between the machine and the dive. The strange part is that by then, Parker had already been inside the corona. April 28th, 2021. On its 8th orbit, the probe crossed a boundary called the Alphen surface, the altitude where the sun's magnetic grip becomes strong enough to own the plasma around it. Below that line, you are not in open space anymore. You are inside the sun's atmosphere, in territory that belongs to the star. The probe's instruments caught the crossing directly. The field strengthened, the plasma changed character, the rules changed. For a few hours, the probe flew through plasma still leashed to the star, wind that had not yet been born. Then it popped back out. It would cross that boundary again on later orbits, and the crossings revealed one more surprise. The sun's front door is not a smooth sphere. The boundary is wrinkled, full of spikes and valleys, a shoreline rather than a wall. When NASA announced that first crossing in December 2021, they put it plainly. A spacecraft had touched the sun. Some people roll their eyes at that phrase, and the objection deserves a straight answer. No, the probe did not land on anything. There is nothing to land on. But the corona is not marketing. It is a measurable region with a measurable boundary, and on April 28, 2021, a human machine crossed that boundary for the first time and proved exactly where it was by the physics it recorded. That first crossing was a toe in the water. December 24, 2024 was the plunge. The record pass, 3.8 million miles above the surface. If that still sounds distant, calibrate it. Mercury, the closest planet, never comes within 28 million miles of the Sun. Parker flew to about 1/7 of Mercury's closest distance, deep into a region no instrument had ever sampled directly, and it did so blind. Remember the blackout from the beginning, near the Sun? The corona's electromagnetic roar swallows radio. For the entire closest approach, the spacecraft was on its own, running stored commands, keeping its shield pointed sunward by itself, one mechanical flinch from becoming vapor. A pointing error of a few degrees would have ended the mission in seconds. The dive lasted through Christmas. The beacon came on the 26th, and in early January 2025, the full recordings of the descent reached Earth. Decades of solar physics had been built by watching the Sun from a distance, like detectives studying a building through binoculars. Now, someone had finally been inside the building. The recordings did not disappoint. They complicated everything. Start with what the camera saw. Parker carries an imager called Whisper, and during the close passes, it filmed the solar wind in the act of being born. Streams of plasma pulling away from the corona, organizing, accelerating outward. Scientists had spent 60 years measuring that wind from Earth's distance, far downstream. This was the river filmed at its source. Decades of guessing what the water looked like upstream, settled by standing in it. Then came the Switchback census, and it turned the newest suspect into the lead. The closer Parker flew, the more switchbacks it found, whole highways of them, clustering in patterns that lined up with the magnetic structure of the surface below, the spacing of the switchback highways matching the spacing of magnetic funnels in the solar surface, the way footprints match a boot. That geography matters. It suggests the kinks are not random turbulence, but are being manufactured down near the surface, plausibly by small reconnection events, the same family of processes behind nanoflares, and then riding outward along the very waves suspect number 1 is built on. Each switchback, as it relaxes, hands energy to the plasma around it. Caught at the scene in enormous numbers, they carry exactly the kind of energy the corona needs. To be clear about what is proven and what is not, switchbacks are now a leading candidate mechanism in the published literature, not a closed case. The honest verdict so far is complicity. The waves, the reconnection, the switchbacks appear to be working together, a network rather than a lone culprit. 3 suspects, 1 conspiracy, and the corona as the getaway car. The probe even caught the Sun taking evidence back. During a coronal mass ejection, one of those billion-ton eruptions of magnetized plasma, Whisper filmed material that failed to escape and fell back toward the star, blobs of plasma raining home. NASA scientists describe it as solar recycling, and some coverage has called it the solar wind making a U-turn. Watching how much of an eruption escapes and how much falls back feeds directly into predicting which storms actually reach us. It is also a reminder of how young this kind of science still is. We have watched the Sun for all of recorded history, and we are only now learning what it takes back. Which raises the question this entire mission was quietly built around. What happens when one of those storms arrives at Earth with our name on it? It already happened once. The year was 1859. On the morning of September 1st, 1859, a British astronomer named Richard Carrington was sketching sunspots when a patch of blinding white light flared on the solar surface, brightened for about 5 minutes, and faded. Less than a day later, the sky over Earth went strange. Auroras, the polar lights normally locked to the Arctic, spilled south over Rome, Havana, the Caribbean. People in the tropics watched curtains of red and green fire hang over their heads, and the telegraph, the only electrical network the planet had, began to fail. Operators reported sparks jumping from their equipment. Some were shocked at their keys. Lines caught fire in places. And strangest of all, some telegraph stations disconnected their batteries and kept transmitting anyway, running on nothing but the current. The storm itself was pushing through the wires. Operators between Boston and Portland spent 2 hours passing traffic that way on storm power alone, and reported that the line actually worked better with the batteries cut out. In places, the night sky burned bright enough to read a newspaper by. That was a planet-sized geomagnetic storm meeting a civilization whose entire electrical exposure was a few thousand miles of telegraph cable. We now run on millions of miles of wire, power grids, satellites, GPS, the navigation behind every plane and cargo ship, the timing signals behind banking. Studies that have gamed out a direct Carrington class hit today, including a 2008 National Research Council report and a 2013 Lloyd's of London analysis, land on scenario estimates of continent-scale grid damage, with high-voltage transformers, the hardest parts to replace, failing in cascades and recovery measured in months to years. Those are models, not prophecies, and worth labeling as such. But the exposure is real, and here is the operational problem. Our main storm monitors sit at a point about 1 million miles upstream of Earth. A fast solar eruption covers that distance in under an hour, 15 minutes to an hour of warning. That is the margin today for deciding to protect continental power grids. Satellites can drop into safe mode in minutes. Reconfiguring a continental grid takes longer than an hour. The math does not favor the defenders. The case for Parker is that the margin can grow. Watch storms being born at the source instead of measuring them at our doorstep, and warning times stretch from minutes toward days. That is not abstract science. That is the difference between a blackout and a near miss. And it is worth sharing with anyone who thinks space weather is someone else's problem. So, where does the case stand? The spacecraft completed its prime mission in late 2025, closing out its planned tour of 24 orbits, closest pass after closest pass at that record altitude of 3.8 million miles. It is still operational, still healthy behind its shield, and the teams are working on what its extended life should look like. The data it has already returned will be argued over for a decade. That is not a failure of the mission. That is the point of it. Science that only confirms what everyone already believed is bookkeeping. The measurements that argue back are the ones that move the field, and this machine came home with a full case file of arguments. The coronal heating case file now has photographs from inside the scene, a suspect caught in numbers nobody predicted, and a mechanism taking shape that ties the old theories together instead of crowning one of them. The mystery is smaller than it was. It is not closed. One more piece of the story deserves to be on the record. In 1958, a young physicist named Eugene Parker submitted a paper arguing that the sun constantly blows a wind of charged particles across space. 2 reviewers rejected it. The idea seemed obviously wrong. The journal's editor, Subramanian Chandrasekhar, a future Nobel laureate, overruled them and published it. 4 years later, spacecraft measurements confirmed the solar wind exists, exactly as predicted. 60 years after the rejection, NASA did something it had never done in its history. It named a spacecraft after a living person. It was a thank you delivered while the man could still hear it. Eugene Parker, 91, watched his namesake leave Earth from Cape Canaveral in August 2018. 60 years separated the rejection letters from that launch. He lived to see it touch the star he had spent his life decoding, and he died in March 2022 at 94, vindicated twice over. The machine carrying his name is still out there, circling the furnace, still listening. Tell me in the comments which verdict you would sign, waves, nanoflares, or switchbacks. And tell me this too: if your power went out for 6 months, what is the first thing you would miss? Because that answer is what this mission is actually protecting. If you want the next case, the James Webb Space Telescope has found objects at the edge of the visible universe that, by every model we had, should not exist. Or stay closer to home, there is a spacecraft 15 billion miles out whose signal grows fainter every year, and the story of its last transmission is coming. Both investigations are already open.